So welcome. For the next few minutes, I'm going to be talking about RISC-V Trace. Specifically, I'm going to be looking at the trace standards, talk a little bit about our experience. I tell people this is going to feel a little German, meaning we're going to get down into nuts and bolts, and we'll talk about nuts and bolts, and it's up to you to figure out what you're going to build. My name is Dennis Griffith. I'm an FAE. I support everyone west of the Mississippi. So if you ask for technical support and you're west of the Mississippi, you're going to get me. Okay, so what is the problem? And it's getting cheaper and cheaper to add more and more cores. And I joke with my sales guy, it's like pretty soon you're going to see the multi-core chips going into toothbrushes to shake the head. And he kind of laughs, but if you start looking at things like the Raspberry Pi, for example, Raspberry Pi Pico, that started out as a 2-core system, and now it is 4 cores. You get 2 ARM cores, and you get 2 RISC-V cores. There's a reason why that's happening. It's cheaper, and people want to have that happening. But that means that you're going to be looking at more and more architectures. You're going to have more and more cores. Debugging is going to become more difficult. You're going to see AMP systems, SMP systems, and you need to figure out what is going on. While that's happening, you're seeing the software stack get more complex as well. Haven't had too many customers have issues with hypervisor, but I'm now starting to see it. And I see slide sets where cars, which I tend to think of cars as actually pretty simple things, you're seeing hypervisors used there as well. And so debugging that environment is going to cause a lot of issues. So when you get those heterogeneous environments, the difficulty of debugging it's going to become very high, particularly when you start looking at those mixed environments. And when you start throwing in security, it becomes a real challenge. This is why you're going to need more powerful debuggers and trace. So a little bit about the RISC-V debug spec. So this has been available for quite a while. A lot of people have been working on this, trying to get something that's very flexible. And I see some people in the room that I recognize that were on that committee. We were as well. It's a great solution for simple to complex problems that you're seeing with RISC-V. And sometimes I have customers start asking me questions about it, and I say, this, you can sort of think of it as an API for the hardware. When they start asking me about individual signals and so forth, it's like, okay, look, this is not how to implement it. It's not what those structures need to look like, but it's how it's going to react and how it's going to behave in the environment. Follow the spec and you'll be okay. They put a lot of flexibility into it. You don't have to go off and create your own scans and so forth because of what's already there. You can talk to different things. You can, through that DTM, you can have just a single core. You can have multiple SMP complexes that are talking to each other. Very nice solution. In addition, it allows for enhancements. You can add things to it. So, why am I going to be talking about trace? So the issue is that when you're in a debug environment, you can stop the core. That's very easy. And depending on the peripherals that you have, you can stop those as well. Problem that you're going to have is you can see this in the picture. You got the engine. You can't freeze the real world in some cases. You're going to have different kinds of bugs when you do this, right? So I have customers that stop the core and they're using an automotive part and it's like the peripherals just run like crazy because it's trying to keep that engine going. Conversely, if you stop that, you stop the peripherals, then your engine kind of blows up. So how do you debug this? This is where trace comes in. So with trace-based debugging, in essence, it's a recording of the execution, maybe that data flow, and you can see what happened in it without stopping the CPU. So you're in scenarios where if you have hard real-time requirements, like the engine will continue to run. I had a mechanic once say the engine was stumbling and they updated the ECU and it fixed it. So if you have problems with your software and it stumbles a little bit, the software takes a little bit of time, you can have problems. But there are also classes of bugs that sometimes you see. I've had people doing just applications, and they would put that together. Unit tests looked great, put it all together, start running it, and it wouldn't run. And it was bugs that they could only see when they were running real time and things were interacting. So you got your code running. Some of the other things you can do with Trace is you can go through and start to optimize. If you have that recording, you can start to look at the timing of those different operations, where your cores are spending your time and what it's doing, and you can start to optimize it. It's like, oh, this function is taking more time than I want, or it's taking a lot of the time. Additionally, with some of our tools, you can collect information that shows what's happening in the real world. So you get some interaction between what's happening outside the core and what is my software doing inside. So that's another application for Trace. And finally, for qualification. So if you're in a safety critical environment, one of the things you can do with it is do a proof that says, yes, my software routines always take this amount of time or less. And so you're good there. And additionally, you can look at code coverage. It's like my testing went through and every function was exercised. I hit every line of code, so I know it's good. So let's talk about the trace specifications. So there's two specifications that you're going to see, the E-Trace and the N-Trace. Before that, there were a couple of proprietary solutions that were out there. These kind of evolved as the work groups worked with those, and those specs became open standards. And you'll see that there's quite a few documents that describe what those look like. You can see some commonality between the two, and you can see some sections where they are different. Please use those, because if you follow along with those, then you have a high likelihood of being successful. The software should just work. So, in summary, I guess, of just those trace solutions, they work, the specs allow for heterogeneous environments, which is good. They are very flexible, so if you want to implement some things a little differently, this is where you get your value add. One of the things that comes up, and somebody was asking, you can actually filter trace. So I guess getting down in the weeds a little bit, one of the issues you have with trace is there's just a lot of stuff that can come out of your application or real-time cores. You might want to narrow that focus. So I only want to look at the needles, not the hay. It also limits your bandwidth, and that may allow you to be successful. Speaking of heterogeneous environments, a lot of customers are mixing RISC-V with ARM. So there's that ability to do that as well. So you can get that information coming out of your RISC-V cores, and you can dovetail that into your core site environment. So here we're saying that Lauterbach supports the latest versions of E-Trace and N-Trace and their various implementations. The specs are pretty new, so as we work with the vendors, we get the systems worked out. And we'll discuss this in a little bit. It's a nice picture showing a complex environment. So one of the questions that I've had even today, okay, what's the difference between N-Trace and E-Trace? We have a little table. You're going to have to decide which is better for your application. And there are reasons for it. This is why you have two specs, because some people want to focus on one aspect and some the other. It really depends on what you're doing. It depends on your silicon design. Okay, so here's an example, small controller. You're seeing that it's based on N-Trace. It has one core. It has that encoder. That's that green blob there. And then it's going to an on-chip trace sync. So very simple. The spec allows for that. Now you have that complex system that you're seeing here, where you have a couple of SMP complexes working together. You have I guess a supervisor or monitor core. Maybe that's RISC-V, maybe that's something else. Those are all blending together, and they come off chip in that blue section of the bus there. So the spec will allow that. I always kind of bristle a little bit when it's like, oh, we need to do something different. And it's like, well, you do. And then the code, we're going to have problems getting all the debuggers are going to have a hard time supporting it, just because we designed to that spec. So this is where I told you it's going to feel a little German. So we're going to walk through and show how you set that up for an N-Trace system. Basically, you start off at the beginning. It's like you have your JTAG interface. You define that DMI. That will go, or excuse me, the DTM that goes to the debug module through the DMI. This is where it starts getting interesting. In Trace 32, you'll define what trace encoder are you using, and then how you bring those together. So the funnels are a way to take multiple trace streams and bring them together in one, and then that finally goes to the sink. And so this next piece is going to be really hard to watch. I know the developers were very proud of the work they did, but it's going to be impossible to see. Basically, what you're seeing is a dual core system. There's a box at the top showing the 2 cores. Now we're kind of playing with it and showing that there's 2 cores. Next, you're going to see a list window that will come up. And I want you to be very, look at the background colors. Right now, it's hard for me to see, but you'll notice it switched between pink and green. Those are the 2 different cores, so you're working with an SMP environment. Next, they're going to show you the ability to turn on and off timestamps, where that's at. Lauterbach tools will actually give you access to the registers, and that's what this window is, kind of showing that it's N-Trace. And we're going to actually start capturing things. So Trace, I get this question from customers. Trace doesn't capture every clock cycle. What it does is it takes milestones. You can tell how long it takes between those milestones because there are counters and so forth. But what you're seeing here are the trace packets. And so this is like the low-level stuff that's coming out. Again, you see that pink and green. So this stream has information from 2 different cores. So you can blend those 2 together. Pretty soon he's going to turn on the timestamps. So you can see that there's timing information. And he's going to show it some more because he knows that there are people in here that worked on this. And so he said, people are going to be very interested. But where it gets real interesting is, at least for most of my customers, they want to see that software. And that is the code that was between those milestones, those trace packets. Again, the pink and green shows the different code that's being executed. This, we call it the trace chart. I tell people it's like a sideways sequence diagrams. I have customers that tell me that they can find bugs just by looking at this, and they can see the shape of their software. What we're going to show here in a second is we're going to bring up a trace list window, and we're going to correlate between the 2. And I realize you probably can't see this that well, but there's a cursor that's going between the 2, and you can select different things, and you'll see them move. And in fact, here he starts going backwards in time. Remember I said it's like a recording? So he's going to go backwards in time. And it gets very interesting because we can look at that and we can tell what the register values are going to be. So you can look at your registers and go back in time and see what that's like. And when you're done with that, then you can start doing the code coverage. And that's going to show up in these bars. I guess the thing to see here is that some of those bars are 100%, and there are some that are not quite 100%, and one that was not there at all. And that meant that your testing wasn't very complete. So those are some of the things that you can do with Trace. So this is the marketing portion where we say Lauterbach has always been out there. We're very engaged with RISC-V and trying to be involved. Here are a couple of examples where we've had announcements of us being involved with Trace and RISC-V. So in summary, the chips are getting more complex. Even the low-end chips are multi-core, and I have customers with hundreds and hundreds of cores on a chip that's in a server, that's in a data center with tens of thousands of different computers. Debug is going to become more difficult. So the debug specification, very flexible. It can scale from the low end to the high end, and including heterogeneous environments. We now have the two trace standards, E-Trace and N-Trace. Those will help you find those bugs that are happening in real time that you need to figure out what's happening. And we have been very supportive of this and trying to make sure that our customers, your customers, or you are successful in finding your bugs as efficiently as you can. So we support that today. I've been showing debug and trace now for 3 years, debug probably longer than that. So stop by our table, talk to us. We have a white paper that you can download if you want more information. Okay? So I'm open for questions. Yeah. There's a mic coming.
When I use trace hardware, like the core site,
Okay.
problem was the trace buffer, like the STM and ETM, is
Right.
wrapped around without any facility. If I don't use any facility, so when I use, if I use your trace proof, can I get the trace in real time, so long time?
Yes. So our tool actually has this mode that, if I understand the question correctly, and let me repeat that so I'll make sure. You want to know if you can get that trace information in real time? Yeah. Okay. So we have a mode called SPY mode. And what happens is if that trace comes off the chip and is collected by our tool, that trace module then becomes a big FIFO. And so the information is getting stored in that, and we start streaming it back to the PC, the host that's running the software. That host software can then start to decode it. It will have to have a copy of the code that's being executed down on the target, and then you can start to see that in real time. Additionally, we have a mode. So I know that there are some interesting use cases. We call it the pipe mode, where instead of decoding that and showing you that on the screen, we can actually run that through an application you might have. I've only had one customer start to go down that path, and he's like, wow, this is complex. It's like, yep, there's a lot of data there.
In that case, can I stop the capturing when I find a specific pattern in the trace, like your trace 32 tool, we can break when memory write specific value, kind of many things.
That's a good question. I don't think I have enough experience to know. I have customers that will start and stop trace with their fingers, and I'm like, okay, you're doing this on a gigahertz core? So maybe, but I don't have a lot of customers that use SPY mode and to see what capability you have. And I see there was another question over here somewhere. Yes.
Yeah, on your earlier slide, you talked about test coverage. Was that a type of code coverage that we could provide to the firmware engineers?
Absolutely. So, and actually that's used quite a bit. Typically what happens is we have a validation group, or not we. My customers have a validation group, and they're just running the code. They don't know what it is. They're collecting that test coverage. They can save that information off to a file and hand that back to the firmware engineers, and then they can go look at that code along with a report and figure out what exactly was happening.
Okay, so the tools provide the code coverage, it doesn't have to be post-processed.
Correct. So if you're sitting there at the tool, it will do code coverage right then and there, or you can save that information off and do it post-processing. Depends on where you're at with that life cycle. Anybody else? Yep.
Rather an answer to this question about triggering, like stopping trace, the spec allows you to stop the trace at an event. You can define an event inside of the core that then it may break. Kind of like a breakpoint, but core keeps going, but trace got stopped to
Yes.
the point, right? So then you can look at it next year, for example. Right?
Yep. That's a good point. A lot of customers will set those breakpoints. I just don't have a lot of customers using SPI mode, so I don't know how that would interact with it. You know, would you get control of it? But yes, very much so. Okay.